Now we can officially start our summer school, and I'm pleased to introduce our first guest speaker for the morning session. Uh, Professor Doyne from Oxford University is a well-known scholar in this field, and he has been a professor in mathematics for a long period, and he is also director of the complexity economic program at Oxford University. Without further ado, please join me in welcoming Doyne.
Salam Kubit. It's a very great. If I can get applause for that, then I should be able to get applause for anything.
That's all.
And that's yeah. But okay, so it's a great pleasure to be here today. I'm very excited to be part of this project that was mentioned, and I thought, what could I say to you today that might be useful? And I think indeed, from what I've seen, the strategy is very good to begin with new, fresh topics in economics. The three workshops are all representing market design, I would say, is one of the things in economics that's really shown the practical value of economics in the last couple of decades. And the other two topics are things that I think show great promise going forward. I'm going to offer a vision today, a bit speculative perhaps, about where I think economics might go. And so I'm going to throw that out. I'm not going to focus on details and not talk too much about the details of my own work, but more try and present the broad vision. Let me also urge you to ask questions as I go along. It always makes for a much better lecture if you're brave enough to raise your hand and say, I don't understand, or could you say more about this? So please do that. Now, let me see if now, so this is the outline of my talk. I'm going to talk, well, you can read it, but I'm going to begin by saying a bit about what standard economic models are and talking about the equilibrium assumption. And then I'll talk about agent-based modeling, which provides an alternative, motivated a bit with some remarks about complex systems, my own ideas about market ecology, and then present some challenges for this research program to go forward and present my vision. Now, I want to just begin with why is economics interesting? I think most of you are economists, so I don't really need to underline this too much, but I would say that everything in society depends on that. And I've seen this in my own life. When the economy goes up or down, everything else rides up or down with it. I think you guys, when you go through, say, the period when the sanctions tightened, and you see what a difference economics can make to everybody's lives, to poor people, and even to the arts and creativity and other dimensions, because when your digestion doesn't work, it's hard to think properly. And I want to present a slightly different definition of, so sometimes you see economics defined as the problem of coping with scarce resources. This is a good definition, but I think it sometimes focuses on the wrong thing. The economy is the process that transforms raw materials and human labor into goods and services. We were hearing that in the previous lecture. It really gets down to things like power. There's physics and the engineering of actually producing these things depends on the economy. And in particular, I think economics has to guide this toward the understanding and improvement of human well-being. Now, there has come to be a standard template for an economic model. And in this standard template, you assume that agents have preferences and beliefs, and then you find a fixed point equilibrium where the agents maximize these preferences according to their beliefs. In the strongest form, the preferences are utilities, and the beliefs are based on rationality. But I would say the program in economics over the past 30 years or so has been to modify the assumptions of this model one at a time by putting in things like asymmetric information, institutional constraints, making perhaps only some of the agents be rational, and attacking things one at a time. But one has to ask whether you need ultimately to attack some of the more fundamental assumptions like equilibrium itself. And I'm going to talk about that today. In particular, I'm going to use as a sort of a reference point what's called a dynamic stochastic general equilibrium model, which is the standard that's used in, say, central banks of the world now for doing policy analysis. And people like this model for various reasons that I'll go over, but let me just say a little bit about how it works. And I'm going to, it in some sense helps to think of it, I would say, as a rocking horse economy. This is a term coined by Andy Haldane, who is the chief economist of the Bank of England. And that you assume the economy is in equilibrium. You assume there's a shock that knocks it out of equilibrium. Then it moves back towards equilibrium as it relaxes from the shock, and that's the part you can compute. And then a new shock arrives and knocks it out again, and that process repeats itself over and over. This is evident in what's called a real business cycle model. So maybe it's worth just looking at a few business cycles. This is an example of a business cycle, or of business cycles. So you see log GNP for the United States. You see it as a function of time since 1955. And you can see there's substantial oscillations going on there. Here's other aspects of the business cycle. And you see in each case, there are these fluctuations going along. So in the DSGE model, all these fluctuations are being driven by shocks. That is, by things that you have no understanding of, that come from outside, that hit the system, knock it out of equilibrium, and then it relaxes back into equilibrium again. Now, while I think this is maybe a sensible starting point for many things, one of the problems with this view is that you've effectively taken off the table really explaining what's causing these swings. Because there has, and I would argue, there has to be some kind of endogenous dynamic going on that's creating these swings. Instead, this dynamic has been made exogenous. The gods somehow provide the dynamics. We only respond to it. And the gods, in this case, you could say it's sociology, it's external events, it's the weather, it's politics. But I would argue that it's actually largely economics that's causing these swings, and we need to understand where these oscillations are coming from. Let me just also mention that there's different kinds of equilibrium. My background was originally in physics, so I grew up thinking about physical equilibriums in which forces balance, a kind of trivial notion. A much richer notion in physics is that of thermodynamic equilibrium, in which, in some sense, things have been interacting with each other long enough that they've reached some kind of steady state as a result. But in economics, the equilibrium is really a strategic equilibrium. That is, it's one in which agents fully consider each other's behavior. So the idea in equilibrium is that I take what you're thinking into account, you take what I'm thinking into account, we both reason all this out to the nth degree, and then we arrive at a fixed point where we've fully taken everything into account and around which we aren't varying. So I'm going to go back and examine that since I think most of you are economists, I just want to say that actually I'm increasingly convinced that there are cases in which you're aggregating things up from the microstructure in which thinking about these other notions of equilibrium may be valuable in economics as well. And so now what I'm going to do is I'm going to talk about why are non-equilibrium approaches needed. In particular, beliefs may not be consistent, and when that happens, strategy dynamics may not settle into a fixed point. So in other words, I may be only reasoning about what you're thinking up to a few levels. You may be only reasoning about what I'm thinking up to a few levels, and as a result, we may not have consistent views of the world. And those inconsistencies may create dynamics so that at one step I think one thing, and then you think another thing, and we keep changing this through time. And I'm going to begin by thinking about a simple Keynes beauty contest. So in this version of the Keynes beauty contest, and you should realize, maybe all of you are already familiar with this, but in Keynes's time, it was common in the newspaper to have a beauty contest in which they would publish pictures of women, and then people would vote on the woman they thought was the most beautiful, but really what it meant was the woman that other people were most likely to consider as the most beautiful. And if you voted for the woman who everybody else thought was, or that, like say, the woman who got the most votes, then there would be a prize, a raffle, in which your ticket would be possibly drawn and you would win a prize. Now in this version of it, instead, well, let me just say that Keynes pointed out that the important thing wasn't the absolute question of which woman was the most beautiful that you really liked. The goal in the contest is actually to pick the woman that you think the most other people would like. So this is an example of that kind of contest. So name a number between 0 and 100, and the winner of the contest will be the one whose guess is 2/3 of the average guess in the audience. So now I'll ask you, what is your guess? So let's suppose we're going to play the game. And so I'm not going to give you very much time to think about it, so think fast. And maybe what we can do, rather than everybody submitting their bid individually, is I'm going to start in bins. I'll start at the top. I'll start at 90 to 100, 80 to 90, etc. And I want you to raise your hand if that's your vote. Okay, and I'm not doing this to embarrass you, but let's go ahead. All right, who votes for the 90 to 100 bin? Okay, who votes for the 80 to 90 bin? Okay, all right. Who votes for the 70 to 80 bin? Not many. All right. Who votes for the 60 to 70 bin? Okay. Who votes for the 50 to 60 bin? All right. I think that's so far maybe the most popular. Who votes for the 40 to 50 bin? Yeah. 30 to 40? Not very many. Okay, 20 to 30? Okay. 10 to 20? All right, and the 0 to 10. Okay, we see the real economists in the audience. Okay, so what is the right answer? Well, this is a study that was done by a Danish newspaper. So this is the right answer for Danes, I suppose, or at least people that read this newspaper. In the sample, I believe there's 30, if my Danish is correct, there's 32,000 votes altogether, so quite a large sample, bigger than here. And what you can see is that the most popular vote was here, about 33, and the winning choice was then just above 20. So what does your vote depend on here? It depends on how much, at least if I gave you more time to reason it through, I think you would have all realized this. It depends on how many levels of calculation you think are going on in everybody else's head. Because the first thing you might note is that if you make a guess between 100 and 66, that since the right answer is the average, the only way you would win if you were voting in here is if everybody voted 100 but you, then you take 2/3 of that, then 2/3 of the average vote would be around 66. So you're not likely to win up in this zone. Now, but then you can go, well, people are thinking, they're reasoning about this, so I've just now lowered, I've eliminated this part, so now we take the average from here to here, and we take the average of that. Well, okay, the average of 66 is around 33, so that might, or no, wait, sorry, I'm doing that wrong. It's around, I don't know, 50, 40 something. So, oh no, sorry, the average is around, sorry, yes. If everybody voted uniformly from here to here, the average would be there, and then you would take 2/3 of that, And you would get that, but maybe you'd think people were still reasoning at 66. You take 2/3 of that, you take 2/3 of that, you can reason through this in different ways, but what you can see is the average is converging towards 0. So that's why I said the hardcore economists were the ones who voted for 0, because that's the rational choice. That is the Nash equilibrium of this game. But what you see is the winning value was actually here, and there was a spectrum. There was actually quite a large mass of people who voted up here. And I think we saw that same thing when we did the experiment here. So somehow, the Nash equilibrium, the message is, Nash equilibrium is not always a good behavioral model for what people are going to actually do. So then the question becomes, how do we find a good behavioral model? And so now I'm going to present a piece of my work on the question of when is the equilibrium system justified, assumption justified. And I'm going to test it using game theory, so similar to what we did just now. We're going to assume there are players who choose one of several possible actions or moves at each turn, that the players receive payments based on the combined actions of all the other players, including themselves. The game is going to be played repeatedly, and we're going to make the players learn their strategy using a standard algorithm for learning strategies. And let me see if, oh yeah. So the question is, what's the typical behavior? So in order to understand what's typical, we're going to construct the payoff matrices at random. That is, we're going to just assume there's some structure such that if I make a certain move, somebody else makes a certain move, we can look up in a table what the payoff, what each of our payoffs is going to be, and we're going to just populate that table with random numbers. And we're then going to try and characterize the long-term behavior of these games a priori. It's a bit like, the goal is a bit like in physics in fluid turbulence. There's a number called the Reynolds number that has to do with the ratio of the shear stress in the fluid to the viscosity. And if I know that number, I know automatically a lot about what the solution is going to be, because if that number is very low, I will have laminar flow, in which things will flow in a very orderly fashion. And if that number is very high, I'll have turbulent flow, in which case things behave randomly. And we'll see something a little bit like that here. So now, one of the intuitions is that simple games should be easier to learn than difficult games. And that, let me just say, from a dynamical systems point of view, that's one of the things I've done in my career. There must be something rather special going on if the fixed points are generically stable. That is, Nash proved there always exists a fixed point, but Nash did not prove that such a fixed point is always stable under perturbations. So we then make up the ensemble of games. As I said, we actually choose random numbers in the payoff matrix, which is called pi here. And we then can populate the payoff matrix pi ij. This is if, and now we're going to do two-player games. So we'll assume there's just two players. So if player I makes one move, player J makes some different moves. If player A makes I and J, and player B makes the opposite set of moves, or sorry, I'm not saying this right. I apologize. I think it's I'm still a little bit jet lagged here. So we will assume we have players A and B who can make moves I or J. And so this is the payoff matrix to player A, if the two players make moves I and J, and this is the payoff matrix to player B if the two players make moves I and J. And we'll assume that we're going to choose the expectation of the product of these payoff matrices so that it's some number gamma divided by n, where n is the number of possible moves. And I'm sorry, we're having some problems with the type font here, but if gamma is equal to -1, then the game is zero sum. Because what that says is that if we make a certain set of moves, if I get one payoff, you get the opposite payoff. So if I win, you lose, and vice versa. And so we're now going to model our learning using something called experience-weighted attraction. And so this is a form of reinforcement learning where players learn strategies based on actions that were successful in the past. And so we assume there's some probability that player mu, I'm changing my notation slightly, takes action I. And so in other words, at each step, I effectively roll a dice to decide which move I'm going to make with some probabilities for each of the possible moves. This factor Q is an attraction of player mu to action I. And then these parameters beta and alpha are parameters about the learning algorithm. Beta is called the intensity of choice, and alpha is the rate at which the learning happens. So just to go through this formula here, this probability that player mu takes action I is the exponential of beta times this attraction, which can vary in time, divided by the sum of all possible values of this. So this is normalized, so it's a probability. And then we take a moving average of this attraction for a given player. I actually should have had mu there, so that we're effectively assume that this player has almost the same attraction they did before, and then you update each time by adding alpha times a sum over effectively the payoffs, so that you're always moving your attraction towards the move that would have given you the best payoff in the past. So in other words, you're playing what on average has worked well before. So, and then we, in this version of it, we assume enough rounds are played before updating the strategy to get rid of the statistical uncertainty so that we can now think about the dynamics of the strategies in the strategy space as the players are learning under this algorithm. Now, this might seem like a really arbitrary algorithm, but Kammerer and Ho at Caltech have actually done a lot of experiments where they test to see how people learn, and this has been arrived at as a reasonable approximation for how people learn when they're playing games in the laboratory. Now, what did we find when we did this? So realize what we're doing. We'll make up a game at random. We simulate the dynamics of the learning strategies of the game, and then we see what happens. And we see that different kinds of things can happen. We can see, in many cases, what we see is that we settle into a unique fixed point. So in other words, we do get to something that's very close to the Nash equilibrium. The players coordinate their strategies and arrive at an equilibrium as we would expect. That happens, as you can see in this diagram, when this parameter alpha is larger, which means that the players are forgetting something about what's happening in the past, because, just to go back a slide, here, what's happening is effectively alpha is determining how much forgetting they're doing. If alpha is 0, then you just accumulate everything that's happened in the past, or in the limit where alpha is going to 0, so that you don't forget anything. But as alpha gets bigger, you start to forget at an exponential rate determined by that. And it also depends on this parameter gamma. So this is a zero-sum game here. This is a game here in which the strategies, the payoffs are uncorrelated. That is, if this is 0, if I win, you might or might not win. It's completely independent of what I do. And up here, this means that if I win, you're more likely to win as well. So what we see is that there's this zone here where we see unique fixed point, but there's another zone here where the games are competitive. If I win, you tend to lose, where we see chaos, and a region up here where we see multiple fixed points. So in particular, let me take you through an example. These are examples. This is an example of a limit cycle. These are examples of chaotic behaviors in the strategy space. So what you see is, if you look at, and I should say that in this simulation, we've simulated this for a game with 50 possible moves. So it's a 98-dimensional phase space, state space. And we then pick a random initial condition, let the players start playing the game, and then we see whether it settles down. Now, if it went to a fixed point, these would just be horizontal lines. because everything would settle into a fixed probability of playing each of the possible strategies. But instead, in these cases, what we see is some kind of oscillatory behavior. And so we see, for example, here, the probability of playing strategy, and here we picked 3 of them at random out of the possible 98 independent strategies. Well, there's 100 possible strategies, but there's a constraint on the sum of each of the players playing them, so that's how you get to 98. So we see that this is actually fluctuating in time, and the behavior in the state space looks like this. And actually, we see other cases, you see over here, where you see here we see something where we see a 65-dimensional chaotic attractor in the state space. And you see the individual strategies. For example, take this one here. This is one of the individual pure strategies, one of the possible 98 moves you can make. There are periods where the probability of making that move is very close to 1, and other periods where the probability of making that move can be 10 to the minus 30. And so you see there's actually fads. There are periods where certain strategies become popular, other periods where they become unpopular. That's changing endogenously through time. It's fluctuating endogenously, even though there's no intrinsic shock being put into this model. It's actually a fully deterministic model. So this is a warning that in something as simple as a 2-person repeated game, you can get endogenous dynamics so that the fixed point assumption in equilibrium that pervades economic theory is simply wrong. It just doesn't work, at least if you believe the basic setup about the learning capabilities of these players. Now, what we do see, though, is there is a regularity to how things happen. There is a big region where it works just fine, and there's another region here where, on the other hand, where you see this chaotic behavior, and up here you settle into multiple fixed points. That is, depending on exactly what the initial condition is, you do land at a fixed point, but which fixed point you land on depends on where you started. And actually, for these large games, you can have hundreds of fixed points. So there's a high degree of uncertainty about where you're going to end up. Yep, please.
I couldn't get that about D. What's D exactly?
What is what?
What's D?
D, okay, good point. Thank you. Very good question. D is the dimension of the attractor. That is, if these are what are called chaotic or strange attractors, and because you started this 98-dimensional space, but the system can settle down into an attractor of low dimension. So if it's a fixed point, the dimension is 0. Now, if the dimension is 1, and this is showing our ability to estimate this, we have to, it's a bit of a technical point to say how we estimate this dimension, but if you settle into a periodic orbit, then you have a dimension of 1 corresponding to a curve. And 3.1 indicates that you're filling just over 3 dimensions in the state space. So it's moving around that out of the 98 possible dimensions, you've collapsed onto only 3. And then finally up here, you're in 65 dimensions. And as you can see, the orderliness of these attractors goes from a fixed point, which really has 0 limit cycle, it's still pretty simple, to 65 dimensions where the motion's becoming effectively unpredictable at that point, because the dimension's so high that even if you were an econometrician and you tried to build a model based on the past behavior, you're filling out so many dimensions in the state space that your model is going to be terrible regardless of how much history you're able to gather. Yes?
What is making those different dimensions, different number of alternatives of the players? How we make
No, we only have 2 players here. So the question is a very good question. Why do we see this chaotic behavior? What causes the chaotic zone as opposed to the other part? And here I have to say we don't really understand. So this is a nice open problem for anybody who wants to investigate it. And in fact, I have a graduate student who's been investigating this for 2-dimensional games. That is, games that just have one of 2 possible actions. And there we're getting some understanding into what's happening. But in these higher dimensional cases, we don't know. So, any other questions? Yes?
That's really naive question, but I need to know what is the gamma parameter exactly?
Right.
Which will redefine it?
Yeah, let me explain it again. So gamma is, let me go back to this slide. Gamma is the correlation between my payoff and your payoff. So when we populate this payoff matrix, so let's just suppose we were playing a 2x2 game to make it simple. This is actually a 50x50 game, but let's play a 2x2 game. So in a 2x2 game, my payoff matrix will have 4 entries. And those entries will depend on your move and my move. So if you play up and I play up, we have 1 entry. I play up, you play down, we have another entry. So I have a 2x2 matrix for me, and there's a 2x2 matrix for you. So that's what these 2 matrices are here. Okay? Now,
That's why when it's -1 is zero sum.
-1 is a zero-sum game, because if for this to be -1, let's suppose I play up, and let's suppose I play up and you play up. All right, now if I'm winning, if gamma is -1, for this identity to work, if I won, you must have lost. Okay, so my payoff's 1, yours is 0. And we do that for every possible combination of moves. So in that case, really, there was only 4 degrees of freedom in assigning the payoff matrix. But in general, what we do is we flip a coin. If gamma is 0, then my coin flip for my payoff entry is completely independent of yours. And then we can dial this to be anywhere in between. So now when we go back to this region is competitive, because if I win, you tend to lose. This one is the opposite, because if I win, you tend to win with me. So this is also telling us that games where we both win together are very different than ones where we win and lose. Okay? Yes?
Low alpha means that people want to keep their strategy even if it doesn't work.
Pardon me?
Does alpha means that people want to keep their strategy even if it doesn't work? What's the point of alpha?
Well, so here what we're doing with this rule here is we're effectively saying the probability of playing a given move, which is determined by this term here, depends on how well the strategy has worked in the past. So, because this is a moving average, so if the better the strategy works, the more you update this term here and the more often you play it going forward. So the way this is actually working between the 2 players is, I notice that when I play one move and you play a given move, that's a good situation for me because my payoff is high. So therefore, I play that move more often because that gives me a good payoff. Whereas, that is, I try to play in such a way that you will play the other move, and then I will get my high payoff because it's a combination of your move and my move that determines how good my payoff is going to be, right? So I try and find the situations that worked well in the past.
How to compute chaos dimension D?
Okay, so that's a bit technical. We use something it's called the Lyapunov dimension, and there's a formula relating Lyapunov exponents, which are a generalization of eigenvalues to the dimension. But it's a little bit technical. But you can see the paper if you're interested. Okay, I'll move on now just to say that another interesting thing we saw with this is we see what's called clustered volatility in the changing in the payoffs. That is, what I'm plotting here is the difference between the payoff for both players as a function of, so it's not the zero-sum case. So the payoff for both players, it's how much did that payoff change from step to step? And what you can see from looking at this plot is there are periods where things are relatively quiet and other periods like this where you see a lot of change going on. This happens to be a characteristic pattern you see in financial markets. There are periods where markets are quiet, there are periods where markets are not so quiet, and And you're just for free getting this property coming out as a generic property of this kind of learning setup, suggesting that the clustered volatility we see in markets may indeed be endogenously generated, and I'll come back to that point later in my lectures. Let me also say we investigated what happened as you add more players. I was describing a two-player game. What happens when we have more than two players? And what this plot here shows is that as we add more players, this is now the number of players, this is the area of the chaotic regime, that area is getting higher and higher. So perhaps not surprisingly, as we add more players, the frequency with which we observe chaos becomes greater and greater. And in fact, if you go back in this plot, what happens is this blue line, which by the way we can calculate analytically using statistical physics techniques, this blue line translates over to this direction, and so you get more and more volume corresponding to the chaotic case, until in the limit where you have an infinite number of players, it completely takes over the space. Not surprising, because of course a game with many players is a more complicated game. Now, I'm going to tell you a joke just to wake everybody up that goes back to, I should have actually told this at the beginning, but the question is, so this is a joke on both physicists and economists. So how did two economists play chess? Well, they randomly choose white or black. That's the only non-deterministic part of the game. And then they argue about whether white or black wins under the Nash equilibrium of the game. Okay, so how do two physicists play chess? Well, they get very drunk. And I know they're not supposed to do that here, but they get very drunk and they start randomly moving the pieces around the board, and they argue about whether the game is more or less interesting under scalings of the size of the board and the number of pieces. So that's, you see maybe a little bit of that flavor in my approach to solving this problem here. But there's actually a real point behind the joke, which is that you see the danger of the Nash viewpoint when you think about a game like chess. Because why is that, the first part of the joke, silly? Well, because we don't know what the Nash equilibrium is. Of course, if we did, then they might, the only thing that would matter was white or black, because you could just look up the Nash equilibrium and play it. But that's not what people actually do. It's a poor behavioral model in that case. Now, on the other hand, just to defend it, you may know the game of tic-tac-toe. It's also called noughts and crosses. Okay, so when I was about 9, I thought that was a really cool game. And, you know, and I was very proud because I thought I was doing better than my friends at playing the game. And I figured out this strategy whereby even if I went a 0, I could get a tie out of the game. I could draw no matter what. And so there was about a day where I felt like a hero. And then all my friends figured out the same trick. And then the game became very boring because all we ever did was draw. So that's a good example where the Nash equilibrium is learnable. I think the key is that the game is very simple. But when you get to more complicated games, you don't always converge to that. Behaviorally, other things can happen. All right, so let me just say, we've been looking at other things in there. Doyne had a very good question of why do we see these chaotic levels? We don't fully understand that. We've been looking at other algorithms, like algorithms that explicitly have level K reasoning built into them. So the two players are actually, usually one player is a bit overconfident, so they assume the other player reasons one level below themselves. And we've been looking at small games and various variations on this. But okay, I just wanted to say that this then is a precautionary tale, that we should beware of assuming equilibria in situations where it may be entirely inappropriate, because if in fact people are just using heuristics, and if things are essentially unpredictable and they're wandering around the state space, just picking out a random fixed point in the middle of all that might be a rather poor way to think about things. Now, in contrast, I'm using this really as a way to motivate agent-based modeling. In particular, I'm going to talk about models that simulate behaviors of individuals and that provide an alternative. So this is a class of computational models for simulating the actions and interactions of autonomous agents with a view to assessing their effects on the system as a whole. And in a sense, all economics models are agent-based models because the agent's a key element of an economics model, of any economics model. I mean, that's why economics is hard. That's why it's a lot harder than physics, because people think. So you've got to find the right way to take into account how people think. And the problem is you're stuck somewhere between the fact that people aren't fully rational on one side, at least when you give them hard problems. I would argue they can be pretty rational when you give them easy problems. But they aren't fully rational, and on the other hand, they aren't just flipping coins either. So you've got to find the right way to deal with this wilderness of bounded rationality, as Chris Sims called it. So ABMs are computational models that explicitly model the microstates of individual agents or heterogeneous groups of agents. And I want to make a side comment here about computation, because this is something I've witnessed in my lifetime. When I was a graduate student at UC Santa Cruz in physics, I had the great fortune that Stan Ulam gave a lecture in our physics colloquium. Now, Stan Ulam's a very famous mathematician. Among other things, I mean, this for better or for worse, he has one of the patents on the hydrogen bomb. So he's a guy who's not only involved in pure mathematics, but also got involved in some very practical, if otherwise very dangerous things. He's somebody with some history. And when the war ended at Los Alamos, he, together with Fermi, another great physicist, and Pasta, another physicist, made one of the first computational simulations of something in physics. They took a model on a lattice where you had particles and springs, and they set it in some random configuration, and they thought they were going to see a relaxation to equipartition of energy. Translated for you guys, it means equilibrium. They thought they would see the system relax to the physics notion of equilibrium, thermodynamic equilibrium that I mentioned. Instead, what they saw were waves propagating back and forth along the lattice. And they spent a lot of time trying to debug their code. It turns out they discovered something brand new just by taking accepted wisdom from physics that was shaped by linear thinking and putting it on the computer. Now, Ulam's talk was on nonlinear dynamics, and he began his talk by apologizing, saying, this is really a very bad term for this, because to talk about nonlinear dynamics is like talking about non-elephant animals. Because in fact, most mathematics is nonlinear, and the reason we do linear mathematics is because it's what we can do. So we're really the mathematician searching for his keys under the lamppost. But really, we need to think about this bigger world. Now, that lecture actually shaped a lot of my life, and I spent a lot of my career putting mathematical systems on the computer and investigating what they do, because that's the only thing that you can really, that's the only way to get solutions. And so, if you're doing galaxy formation or fluid mechanics or lots of things, computation has completely revolutionized the way things work. That's less so in economics and social science. Now, why? I would say there's two reasons. There's a good reason and a bad reason. The good reason is that the elementary processes aren't understood. If I want to simulate galaxy formation, I have the advantage that the laws of gravity are well known. If I want to simulate economics, the laws of human reasoning are not so well known. So okay, we need to solve that in order to do a good job of this. The bad reason is that I would argue economics was colonized by mathematicians who don't value computation. Mathematicians view that as somehow dirty or not, certainly not a way to publish your paper in a top journal. It's a cultural thing. And I think one has to fight against the cultural thing, because ultimately, going back to my very first slide, our duty as economists is to really understand what's, fostering our well-being, and we should be completely agnostic about methods. Elegance, in my view, is much less important than actually having a correct model. Now, I'm going to now give you a few examples of agent-based models to go forward on this. So I'm going to give you a couple of very simple examples drawn from my own work. In particular, this first one is looking at systemic risk in financial markets, which occurs when the activities of individual agents cause unintended consequences due to their collective interactions. And so, and in fact, this relates to what's called microprudential versus macroprudential regulation. Let me explain what those words mean. Microprudential regulation, which I would say is mostly what goes on now in financial markets when you look at things like Basel IV is mostly microprudential. You do something like a stress test for a bank, you're really taking that bank in isolation. You would say, given the rest of the system as it is, what conditions would cause this bank to fail, and what actions should this bank be taking by itself, assuming the rest of the system stays constant. Macroprudential regulation, in contrast, you have to think about the systemic interactions. So you have to think about the fact that if this bank does something and the other banks are doing something in tandem, you can have a collective interaction that may make things, may mean that the action that the individuals are taking in isolation, the macroprudential correct response is very different than the macroprudential correct response. So I'm going to give you an example, a rather dramatic example where that's true. And in fact, one of the things that I found, and others have found as well, is that oftentimes actually macroprudential risk control can create, no, microprudential risk control can create macroprudential risks. And so there are various channels of contagion in financial markets, networks of counterparty exposures. So that is if I own something, if I own a given stock, and I'm a bank, and my bank in its portfolio has a given asset, and Doyne's bank has the same asset. If my bank comes under stress and starts selling the asset, I depress the price of that asset, which then affects Doyne's portfolio and might cause him financial problems, and he might have to start selling the asset too, because now he's under stress, and now we have a systemic effect. Another example is overlapping, sorry, actually this was for overlapping portfolios, was what I just explained. Networks of counterparty exposures is I lend Doyne money, he lends somebody else money, and now we have a network of exposures such that if one of us defaults, we set off a cascade because everybody else is depending on everybody else paying them back. And then there are other possibilities, but these are, I think, the two main ones, and ones I'll focus on here. In fact, I'm going to really focus on the overlapping portfolio exposure. And so key factors are dynamic effects, which I'll focus on now, which come from things like herding or dynamic risk control and actually cause dynamic contagion, versus network effects, like you can have a network effect because you're connected to a systemically risky institution. As I said, this can be through loans or common assets, and it can even happen within a firm. And finally, I'll come back later on in my talk to talk about ecological effects. Now, I guess I already explained this microprudential, macroprudential trade-off, and I want to say a little bit about leverage cycles. So the idea of the leverage cycle goes back to a fellow named Hyman Minsky, who talked about this during the 70s. And the idea is that somehow during calm times, leverage goes up. So let me unpack what this means. During calm times, firms begin competing for profits because not very much is happening, people aren't taking losses, they're making small profits, but they want to make more profits than their competition, so they take more leverage. What does leverage mean? Leverage means you buy assets with borrowed money. So, for example, it might sound like a ridiculous thing to do. You're going to buy assets with money that you borrow, but actually, at least in the West, you typically will, say, buy your house using borrowed money. When I bought my house, I put 20% of the value of the house down, and I borrowed the other 80% from the bank. So I now have a leverage of 5-to-1 because the ratio of the value of my house, 1 to the amount I put down, 20% is 5. Okay, so during good times, leverage tends to creep up. And as leverage creeps up, Minsky said, wasn't totally clear about why, but things become more unstable, then there's a crash, and then you repeat this cycle again. And this has been amplified on by my colleague John Giannakopoulos, who has a theory that involves heterogeneous investors and optimists who use more leverage. And then when bad news comes, that bad news gets amplified. Now, I'm going to present a mechanism that makes Minsky's idea very concrete and shows that it's even simpler and requires even less than what he imagined. So first of all, I just want to, here's a slide to illustrate that credit cycles are something real. So this is the leverage cycle again. Credit cycle, it's the same thing. You see now more than 100 years, and you see the credit growth here. So you see there are eras where credit becomes more widespread and easier to get, other periods where credit's hard to come by. Right. And there's a large literature on leverage cycles. I'm not going to go through here. But I do want to explain a key fact. If you're a passive investor with your leverage greater than 1, when prices drop, the leverage goes up, and when prices rise, the leverage goes down. So why is this? Well, it's because leverage is the ratio of your risky assets to your assets minus your liabilities, that is your equity. So if the leverage is greater than 1, your risky assets take a hit here in the numerator. They also take a hit in the denominator, but because you're subtracting something off in the denominator, this is smaller, so you end up with an amplification. So if I'm leveraged, prices drop, my leverage goes up. Now, here's a picture to motivate what I'm about to talk about, in which we plot the leverage for US broker-dealers through historical time. So we're starting here at about 2002, and we're going up to 2014. And the black curve here is the realized value of their leverage versus to where they, rebased value of their leverage versus to where they started, or versus to this point in time. So whatever leverage we had there, we'll just call it 1, and then we look at the relative change in the leverage. So what we see is that, well, and actually let me explain the other two curves. This is the value of a stock market index, and this is volatility. So what you see in this picture is that during this period, in the lead up to the crisis, we saw stock markets climbing, we saw leverage climbing, and we saw volatility slowly dropping. Then around in here, we see the stock market peak, we see leverage shoot up, and then we see volatility spike. And so I'm going to present a very simple model that explains this kind of behavior. And unfortunately, I can see I'm having my slides a little out of kilter here, but it doesn't matter too much. So we assume the bank has some leverage target, and this has empirically been shown to be true. Investment banks, broker-dealers, tend to, at a certain point, have a leverage target. So that is, if, and this explains it here, if their current leverage, lambda prime, is under their leverage target, they borrow some amount delta B, and then they buy delta B worth of that asset. Okay? So basically, they borrow if they're under in order to hit their target. Similarly, if they're over the leverage target, they sell some assets and pay some of their loan back so that they keep their leverage at the same place through time, or at their target through time. And so now, in this model, the bank's going to trade with a fundamentalist noise trader who's a passive investor who holds some fraction of the asset, and that fraction will vary randomly. Now, let me just mention commercial banks versus investment banks. So Adrian and Shin wrote a paper where they showed that commercial banks use constant leverage targets, whereas investment banks use what are called procyclical leverage targets. So that means, procyclical means that when the leverage goes up, procyclical means leverage goes up when prices go up and vice versa. So in other words, when prices go up, they tend to hold more leverage. When prices go down, they tend to hold less leverage. And I'm going to define that a little bit differently here. That is, I'm going to call a policy procyclical if basically leverage increases when volatility decreases and vice versa. And I've actually seen this change during my own time as working in finance, when I started the company, a prediction company, initially we were managing assets based on face value. So the bank would tell us, you get to take positions of this face value, and that would determine our risk. Then we went to daily standard deviation, and then we went to what's called value and risk. And value at risk is inherently procyclical, and I'll explain what that means in this slide. So under a value at risk risk management policy, what happens is that as volatility goes up, your leverage target goes down. Which is kind of sensible when you think about it. From a microprudential point of view, it's perfectly sensible because volatility is quite persistent. So if volatility is high now, that says things are riskier than they normally are, which says I should take lower positions because I should be more cautious because risk is high, and vice versa. So from a microprudential point of view, this makes perfect sense. So this would be Basel II, or value at risk policy here in the blue line. The dashed line here would be a policy that just takes constant leverage. So this is what the investment banks are doing. This dashed line here is what the commercial banks are doing. So we're going to now ask what happens when you take these kind of leverage targets. So in other words, we're going to make a simple model. And let me just point out before going forward that leverage targeting is inherently destabilizing. Because just think about it. Remember the fact that I gave you a moment ago. The key fact, when prices drop, leverage goes up. Okay, so if I'm doing a leverage targeting, even if it's constant, when prices drop, my leverage goes up, which means I'm selling. So that means I'm going to be selling into a falling market. So in other words, I'm amplifying the drop that's already happening. And similarly, if prices rise, I'm buying, and so I'm amplifying that too. And using mark-to-market, what does that mean? Well, mark-to-market means every day I go along, I look where the price is, I mark my portfolio to the price. So I'm constantly updating my portfolio. That will exaggerate this. So in fact, we discovered when we were building an agent-based model we built an agent-based model, and I'll show you the slide in a moment. We built an agent-based model where we had banks. The banks were managing multiple assets. They were doing leverage targeting, and we discovered, well, the system just blew up. So we had to add in fundamentalists just to stabilize the economy. Because fundamentalists, in contrast, when prices drop, fundamentalists say, this asset's undervalued, so I should buy more of it, so they buy more. So they tend to be stabilizing. Now, so we did a simulation, and our first simulation, we're looking at our stock market and our simulated economy. And I won't tell you the details about this, because they don't matter too much. But we see a plot that looked like this, a kind of a random looking behavior. And now we said, okay, what happens if we introduce Basel II? So we now had all the banks manage their assets using Basel II, and to our great surprise, we saw this behavior here. We saw a slow run up in prices, followed by a crash, with another run up in prices and a crash happening in a somewhat irregular way. So we said, what's going on? So we began simplifying. We said, all right, what if we only reduce it to one asset? What if we only have one bank? So we kept simplifying things as much as we could. And we finally got a model that had these three simple assumptions in it. We first of all have an exponential moving average of the historical volatility as being the way the volatility estimates are made. So in other words, the representative bank, because we're just going to have one of them now, we just have one bank and one asset, one risky asset plus cash. So the bank goes along and they just take a historical average of volatility over the last couple of years. Well, why do we do that? Well, that's because that's what people do. If you just go start asking how people estimate volatility, that's how they do it. And the time scale is typically a couple of years. Then we put in the Basel II risk management rule. And then we made a very simple price formation rule. And in the very simplest version, and I'll do the simple one and I'll come back to a slightly more realistic one, we just assume that increasing leverage means that people are buying, therefore the prices must be going up. So we put just these three very, very simple, and I would argue pretty uncontroversial components. We can actually reduce, the whole model becomes a dynamical system, a simple map of the plane into itself, where we could use various things as the axes, but down here at the bottom, essentially this parameter, the Z1, is the volatility now, and Z2 is the volatility, actually, Z1 is the volatility last time, and Z2 is the volatility this time. So we have a very simple mapping of the plane into itself, and you can see these equations. This is the equation that says that this is the equity, this is the leverage target. So as the leverage target goes up, prices go up. This is volatility. This is just a moving average of historical volatility. And this is the Basel rule, where we've introduced a free parameter B to allow us to vary from the Basel rule to things that are less procyclical. Like if you make B equals 0, this becomes constant leverage target. It's what a commercial bank does. And notice there's a parameter here, alpha, which has to do with how aggressive the bank is being in trying to make profits. The bigger alpha is, the more risk they're taking. Okay, so now if we just put in, and by the way, this parameter sigma 0 just puts a limit on how much volatility you can take. So to make things simple, we'll put in B equals minus a half. We'll put in sigma 0 equals 0. And we now can look at what happens both as a function of time. So here you see price versus time. So we see the price going up and down in time. And here we see a state space view. That is, we have the volatility last step versus the volatility this step. And what we're going to see is that as we have a bubble followed by a crash, and what that will look like in this picture is that when the crash occurs, we're going to see the point kick out, then we're going to see it fall down like this and kick out again. So let me play the animation if it works. So now you see the bubble happening and the crash. And so now the crash, and then it slowly goes down this stable manifold. So it repeats this again and again. Now what's happening is that in dynamical systems, this would be called the unstable manifold, and this is called the stable manifold, and there's a fixed point sitting down here. So there's an equilibrium down here. But this equilibrium is unstable. So in Minsky style, although it's even simpler than what Minsky said, during the bubble, things are nice and stable. You're settling down the stable manifold, but you're getting closer and closer to this fixed point, and this fixed point has the property that there's a stable direction and there's an unstable direction because the eigenvalue, there's a positive eigenvalue of this fixed point. So when you get down, the closer you get to the fixed point, the more unstable things become, and finally any tiny little disturbance will kick things out and cause them to make this fluctuation. So this is happening again and again. Now, so let me make the model a little bit more realistic so we can use it to do some thinking about policy. So we add in a key additional ingredient. We add in this unleveraged fundamentalist, and we make price formation more realistic. And we also allow the trading frequency of the fundamentalist to follow what's called an exogenous Garch process, meaning that we're assuming for some exogenous reason we're going to have periods of high volatility and periods of low volatility just due to what those guys are doing. So, and we put that in actually so that it would make microprudential sense for the bank to be following Basel II. So from a microprudential point of view, that's the right thing to do. Now, so this is the way the model works. We have a fund, we have the bank, we have a shock coming into the fund. The bank and the fund are trading with each other for the asset in the market, and we're updating prices using market clearing. So this is the model, and this is the model now written out in more detail. I'm going to just skip over this because I don't think it matters. Well, I'll say a little bit about it. This is the perceived risk, as before, historical moving average of historical volatility. This is how much the fund invests. This is the price. This is the ownership of the asset between the fund versus the bank. These are the liabilities, and now we have to complete the dynamical system, have an equation for the lag price. And we now have two key parameters in the model, alpha, which controls the risk that the bank is taking, and B, which determines how pro-cyclical the policy that the regulator is imposing on the bank, or the bank could be imposing on itself. And so now what do we see? We see that, we see that from a linear stability analysis, so this is the unit circle, we start out when alpha is small inside the unit circle, and as we increase alpha to take more risk, there's a point where this destabilizes. So we go from a fixed point, so we're at the fixed point equilibrium inside here, and then this thing suddenly destabilizes, and now we see a finite amplitude chaotic oscillation suddenly appearing. So that as we go from a situation, if you look at the noisy time series, where things look like this, pretty stable, to where things look like this and become quite unstable. And so this is what the price is doing, this is what the leverage is doing. You can see they're oscillating up and down in tandem. Or in the deterministic limit, where we turn the noise all the way down, we go from a fixed point to what turns out to be a chaotic oscillation. And the key point is that you go from here to here suddenly. A tiny change in that parameter alpha, you can be stable, you just go, well, let's just take a little more leverage. And then suddenly the whole system starts oscillating. Now, so this is a picture of the strange attractor. This is what it looks like in the state space. So you see an oscillation in perceived risk, ownership, and price. Or if you slice through this attractor, you see these fractal folds illustrating the chaos part. And in the parameter space, so remember this parameter B allows us to vary from B equals 0, which would be constant leverage target, to B equals minus 0.5, which would be value at risk, or the Basel policy. There's a stable parameter region here where you're at a fixed point, but then there's a critical leverage, in this case around 9, where you get a leverage cycle in this domain, or things can become completely unstable. So the point is, a tiny movement across here can move you from a stable world to an unstable world. Now, we can also then investigate what the optimal policy is. It turns out that it really depends on the parameters. In a low market impact regime, that is where the banking sector is small, or where their leverage is sufficiently low, then the Basel rules are actually optimal, because microprudentially, the fundamentalist is determining most of the dynamics, and they can afford to follow Basel II. It's actually the right thing to do. But in a high impact regime, where either the banking sector is really large relative to the fundamental sector, or where the banking sector is taking very large leverage, then a constant leverage is the best policy to follow. And that is, as you're varying B, this would be the case where you're taking high impact, the banking sector is big, constant leverage gives you the lowest risk, versus versus the low impact regime where that's the best policy to follow. Now, it also turns out that the other way you can improve things is to make the adjustment dynamic slower. Rather than requiring that the banks stay right on their leverage target all the time, you give them some slack. So you give them some time to achieve their leverage target, so they vary things more smoothly. That generates less endogenous instability, and you can just simply see that that stabilizes the system. So from a model like this, I wouldn't want to say that the model is, and by the way, I meant to mention something rather important back here. In these pictures here, the units are actually now in years. So we've actually calibrated the model against the real world, because we know things about the time scale, and we can make assumptions that are reasonably close to what was actually going on leading up to the crisis. And what you see here is the time period for this oscillation is the order of 10 to 15 years, depending on the precise parameters that you pick. So that is, going forward, we're actually capturing this dynamics on roughly the right time scale and actually roughly the right leverages, so that we see something that looks very much like this picture coming from our model. And so in conclusion, I don't want to say that this mechanism was the cause of the great moderation in the crisis, but what I think we can say is that it's actually sufficient to have caused it. And the housing bubble in the US may have just been the spark that triggered the crisis to happen. And back to my broader point, this was an example of a non-equilibrium behavior where the system is not undergoing fixed point dynamics. Now, I think I should pause here and see if there's some questions. Anybody brave enough to ask a question? Thank you.
Okay, well, the thing I was thinking about was that is there any effect between these groups? I mean, if one policy is better working than the other, is there any possibility? Have you imagined that somebody would change its strategy from being fundamentalist, going through, working as a Basel?
Yeah. So the question is, asking the question of who's actually making better profits, in a sense, and would we expect that people would change from one behavior to another, and that might, fundamentalists to acting as an investment bank, and might that alter this?
Yeah,
so the answer would be we haven't really, we have looked at this. I think my recollection is that on average, actually, in this world, I'm pretty confident about this. The two players, on average, are making the same profits, though at different points in the cycle, this is varying. And it would be interesting, we have not put in something that allows them to change based on profits. We're putting in fixed rules at this point. I think let me actually rephrase your question in a little bit of a different way. I presented this in front of somebody who is from the Bank of International Settlements, and their response is, well, but if the agents are rational, they would understand this dynamic, and then they would alter their behavior. And I agree that's a fair judgment, but on the other hand, we're the first to publish this paper. People seem to have not understood this. If they'd understood it, they didn't publish it, although I will say that Charles Goodhart and some others in about 2003 wrote a paper warning generically about instabilities due to Basel II. And I think they were thinking of something along these lines, but in a sort of a Minsky qualitative way. So we're just making that logic precise. People didn't, for whatever reasons, they didn't figure it out before. I do think that people understand a lot better going forward what's happening, and I'm hopeful that it won't happen again, precisely because people now understand this better. But I think this is just a good example of how we need to understand things. Now, in a world where the agents were perfectly rational, we cannot say this for sure, but I think that you would generically sit at this fixed point. But the question, I think my conjecture would be that as the agents become more and more rational, they have to be infinitely rational to guarantee that they're at the fixed point. And when any epsilon deviation from rationality will eventually cause this instability to create an oscillatory behavior. But that's a conjecture.
Yeah, that's true. But if we assume that people are partially rational,
yeah,
and then we can actually put some parameters to value that rationality and say that's okay. For instance, if it's 1, people are fully rational. If it's close to 0, they are partially rational, close to be irrational. Yeah. So what happens when this parameter changes regarding our equilibriums? Because there are some heterogeneous agent models in, Chiarello have worked on it. So Holmes and they're both different. There are fundamentalist chartists and other groups, but never the parameter that measures the amount of rationality was significant in those papers. I was just
Yeah.
wondering that.
Well, so I think you're hitting on something that's a very interesting topic for research. Actually, my ex-student, Christoph Imans, and I, he's at the LSE now, and I are thinking about ways of trying to do precisely this, in fact. So it's an open question. But I think it's at least widely believed that this does depend on your assumptions about rationality. And I'll note that even in like, there's a DSGE model by Adrian and Boyarshenko that sees some behavior that's a little bit like what I'm showing you here. Not quite as clean, it's harder to calibrate and so on. But it's in the DSGE framework, but when you look closely, the key thing that's in there is irrationality that's driving the oscillatory behaviors. So,
Okay.
But not well understood. Questions? Yeah.
So, studying dynamical systems, it's kind of like time series analysis of what the history has been. For instance, the price mechanism that you consider is a function of leverage and asset prices. So this is an asset play, an extension of leverage and playing with assets as investors. There is no discussion of the price determination for those assets as it relates to the real economy. I wonder if the actual shapes, the time dimension that comes through by looking at these processes can change dramatically depending on where leverage is being extended, who the banks
Yeah. Okay,
lend to.
so let me rephrase the question a little bit. I think that there's no real economy in this model. And if you think about the real economy, it might matter. So I'll amplify the question a little bit. In fact, some people, and this is a proposal I think is quite a good proposal, argue that we had a very different standards for lending to the real economy. If you come to me and you want to build a dam, okay, so you were talking about dams and electricity. So you want to build a dam, I go, okay, that's the real economy. I'll lend you money, and I'll actually extend much more credit for you for that than if you come to me and you say, well, I want to do some speculative trade on some swaps. And I go, well, okay, for that, I'm not going to give you very much leverage. And I actually think this is a very sensible proposal, and it's one of the things we're trying to test. Let me just comment that this model, this earlier picture I showed you back here, was actually based on a model that had some real economy in it. One of the things we stripped out was the real economy because we saw it didn't depend on that. This oscillation is driven solely from the financial side, but so in the end, we didn't need to worry about it. But one needs to worry about instabilities flowing back both ways. My belief, but this is something, again, that I think is an important topic of research, is that the instabilities tend to flow from the financial side to the real economy rather than the other direction. And, you know, if you go through, say, the book by Reinhardt and Rogoff, This Time is Different, they historically categorize recessions based on whether they were financially driven. And a large fraction, and the worst ones are financially driven. And I worry that even some of the ones that aren't categorized as financially driven actually probably were, because we weren't able to see the financial stuff that drove them. More questions? Yes?
To see the policy implications of your model, to reduce these fluctuations, I think we need more fundamentalists, or some people may call them crazy people, because they act take more risk in the risky times. But maybe the government should do this.
Well, I don't know. I guess I think, so the question was, maybe we should encourage more fundamentalists because they're taking risk. They're taking more risk during risky times. Yeah, I think actually capitalism works pretty well here. I mean, Warren Buffett is one of the richest people in the world, and that's what he does for a living. And there's a lot of other guys who are not quite as rich as he, but are pretty rich, that have done that. You know, it's a long-term bet. You say the asset's undervalued. They spend a lot of time actually looking at the company itself. Is this a good company? Are they going to continue paying good dividends? And that's what they make their bet on. So they bet on the skew between the popular investor, who might be investing based on a trend, and the fundamentals of the company. So yes, they take risk, but over the long term, they make pretty good returns. So I think that works pretty well, in fact. Now, I think the more important thing to do is to regulate the risk-taking by the banks, because that's the destabilizing side. So I think if we can regulate that, then we can keep the system stabilized. But it's a good question. Any other questions? Yes? There's a question in that corner there.
So basically, in the industry, from what I understand, in the new editions of Basel regulation, there are two measures of how to require banks to allocate capital against the risk. One is value at risk, and another is leverage ratio. And currently, in the industry, basically, many people say that leverage ratio becomes a limiting factor. And basically, it becomes more important for banks to look at the leverage rather than the actual value at risk. And many people in the industry think it basically pushes banks to move into riskier and high yielding assets while keeping the same leverage themselves. What do you think? Do you think it's a smart move to basically regulate banks by leverage as opposed to value at risk or not, given this?
I do think that's smart, and I was going to just show in my slide. So in this slide, here's the formula. This formula actually has both parameters in it. So regulating their leverage means you hold the leverage itself down here. So this corresponds to this parameter sigma 0. Versus their value at risk, you just impose a cap on. You value at risk, you let them use this formula, and pure value at risk would not have the cap. I guess is the way to say it. I think the cap is quite important, and so. Yeah, I think it's very sensible that they're doing that. Now, it turns out that liquidity is also a major problem, and so this isn't the only thing you need to worry about. You really need to worry about the fact that there are hierarchies of assets ranging from highly illiquid to highly liquid, and so there's also been a lot of focus on what balance of liquidity of assets banks should hold. This is another important area where, once again, the devils are sort of in the details. Now, I'm going to, I think, wrap things up here. And so I think this is actually a good place to stop. Let's take a break. Then I'll come back and say a little more about this and go on after the break. Thank you.